Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, working as a professor of chemistry in the University of Delhi. Today, we are going to talk about the module Chemical Force Microscopy, abbreviated as CFM, and we shall be talking about the instrumentation part of this. This will come under the paper of Surface Analytical Techniques Part 1. After going through this module, you should be able to very clearly understand three factors. One, introduction. Second, dealing with principles of this. And finally, with the schematic drawing of the CFM setup. Well, when we come down to the introductory part, one finds that a typical force microscope consists of an integrated cantilever tip, this assembly interacting with the sample surface, a detector that measures the displacement of the cantilever, and feedback electronics to maintain constant image parameter such as tip sample separation or the force. The most popular and versatile detection scheme in AFM is through optical lever deflection. In this scheme, the vertical displacement due to normal forces and the lateral twist due to friction of the cantilever are measured using a quadrant photodiode. Force values are calculated from the nominal displacement 1z or tilt angle theta of the cantilever from its resting position. With an instrumental sensitivity on the order of 0.1, one can measure this, and a minimal forces in the range of 10 to the power minus 13 to 10 to the power minus 8n, depending on the cantilever stiffness, can be measured. AFM can, in principle, measure molecular interactions ranging from weak van der Waals forces, that is less than 10 to the power minus 12, to strong covalent, that is 10 to the power minus 7 n bonds forces. In practice, the displacement and the corresponding force between these compression is limited by thermally excited cantilever vibrations and the optical and electronic noise on this side. In the measurements, if the measurements are conducted in ambient air or liquids, the thermal noise is especially important because sometimes if it is not controlled, it interferes with the proper measurement. Chemical force microscopy is what is being discussed here, and this is for instrumentation in particular. The principle which is involved is the following. The magnitude of intermolecular interactions can be accessed directly in an adhesion measurement. The adhesive interaction between different functional groups is determined from force versus sample displacement curves. In these measurements, the deflection of the cantilever is recorded during the sample approach withdrawal cycle. The observed cantilever deflection is converted into force using the cantilever spring constant. Here, the way the pattern looks like and the graph works out for force and adhesive force in terms of distance has been given on the right side of the slide. You can even calculate the slope, which gives K spring parameter, the force constant of the spring. The other force versus displacement changes are also shown. Typical force versus sample Z displacement curve has been given above in this slide. At large separations, no force is observed between tip and sample. At short distances, the van der Waals attractions will pull the tip abruptly into contact with sample. It jumps into the contact point and jumps very quickly. After that, the deflection of the soft cantilever tracks the movement of the sample, and this leads to linear compliance regime. Hysteresis in the force between tip and the sample is observed when the tip is withdrawn from the sample. The finite force necessary to pull the tip off the sample, this surface corresponds to the adhesive force between functional groups and on the surfaces of the tip and the sample. Whenever the force gradient exceeds the cantilever spring constant, the system becomes mechanically unstable and cantilever jumps occurs. The pull-off force determined from the jumps in the sample retracting trace corresponds to the adhesion between functional groups on the tip and the sample surfaces. Electrostatic interactions. Adhesive interactions between oppositely charged monovalent functional groups have also been investigated. The electrostatic contribution to the attractive and repulsive forces between charged surfaces has been studied previously using SFA and force microscopy. These studies have probed the long-range Coulombic interactions that occur between two charged surfaces as they approach one another. In the present study, we were concerned with the role that electrostatic interactions play as two surfaces just separate, that is, the contribution to adhesion, rather than the effect at long distances. To study this electrostatic interaction, we utilized monolayer of 1:1 mercaptone dicoinic acid on the probe tip and hymonopropylenic thiocylane on a silicon substrate. Simple amines and carboxylic acids are well known to be ionized in aqueous solutions under neutral conditions. Although the pKa of the acidic and basic groups on SAM surfaces shift by approximately 2 pH units higher and lower respectively, for they still should be ionized in solution. Histograms of the adhesion force recorded in deionized H20 at pH 6.5 and in 0.3 molar NaCl solution, pH is 6.5, using blunt tips are shown hereby in the figure. The mean adhesive force between these oppositely charged groups in 14 units in water but decreases to 4.1 units in 0.3 m sodium chloride. This salt concentration reduces the characteristics length scale. Along the significant drop in the length scale of the interaction, we found that adhesive force drops by a factor of 3 units. The strong decrease in the measured force with increasing ionic strength suggests that in pure water, a significant component of the total force arises from charge density summarized hereby. This gives a schematic diagram or drawing of the CFM setup, that is, setup of chemically force microscopy. This has been shown in the diagram and it indicates the way it works. The sample rests on a piezoelectric XYZ translator. A laser beam is reflected from the backside of the tip onto the photodiode to measure two types of tip surface interaction. When the sample approaches and touches and is withdrawn from the tip will move up. It will move up and down in response to surface normal forces Fz, resulting in the vertical deflection signal Vz. The cantilever will twist in response to a frictional force, which we have designated as Fx, yielding the lateral deflection signal Vx. The inset illustrates the chemically specific interactions between gold-coated CH3 terminated tip containing an acidic terminated region of a sample.
Contact trapping, peak force tapping, and interleaved modes have been described. The first AFM mode invented was the contact mode, developed by Binning et al. In 1986. We have ordered it tells in previous slide. While scanning with this mode, the tip is constantly in solid contact with the sample surface under a directly controlled force. This enables advanced electric AFM modes that requires a closed circuit such as conductivity measurements, the carrier profiling, and dielectric mapping. The main disadvantages of this mode is the high shear and imaging force that can cause tip wearing and sample damage. In the early 1990s, tapping modes, also known as AC mode, was introduced to address this disadvantage. Tapping mode relies on the mechanical resonance of the cantilever during imaging. The cantilever oscillator at near resonance frequencies, while the tip either only intermittent contact mode or never non-contact mode contacts the sample surface. In this mode, the set point for the feedback loop is based on the typical parameter of resonance oscillation. Example like amplitude, frequency, or phase, as these parameters are highly sensitive to tip sample distance. In addition to topography image constructed from the phase shift with respect to the sinusoidal driving wave provide additional information about the sample properties. Though this information is often convoluted. In 2009, a non-resonance intermittent contact mode based on the fast capture and real-time analysis of triggered force curve was introduced. A force curve records the force on the tip as it approaches to and retract from a point on the sample surface. When the force reaches a user specified trigger value, the system records the height for the pixel and the tip retract. The trigger value is the maximum force or peak force of each force curve or of each tapping cycle. This peak force is used as the set point in this mode, and this mode is well known as peak force tapping, in short called PFT. Before the introduction of this mode, its legacy force volume imaging had been used extensively in biochemical and polymer mechanical investigation. FV is a slow imaging mode limited by the typically limitation result from the fact that the Z position is modulated by the triangular waves, so that a slow ramp rate is required to avoid unwanted resonance at the turnaround points of the wave. Different from FV, Z modulation in PFT is sinusoidal at low frequency of hundreds of hertz to a few kilohertz. This higher frequency allow imaging speed that are comparable to traditional tapping modes. For example, at scan rate of 1.5 Hz and a pixel resolution of 512 sample per line, a PFT frequency of 2 kHz is sufficient to guarantee greater than 1 force curve at each pixel. More importantly, with this sinusoidal modulation, as the tip approaches to the sample surface, its speed approaches zero. Therefore, linear, stable, ultra-low force control can be realized and automatic image optimization is possible. In addition, the real-time analysis of the captured force curve enable the simultaneous determination or quantitative nanomechanical information at a normal AFM scan rate. This combination is another widely adopted mode called PF-QNM, where PF and QNM stand for peak force quantitative nanomechanics, respectively. The mechanical information typically include modulus, stiffness, adhesion, deformation, and dissipation energy. The low PFT frequency also permit simultaneous nanoelectric measurement. During each PFT cycle, the tip is in direct contact with the sample surface for typically nearly 100 microseconds depending on the tapping frequency and amplitude. A sensor circuit with the bandwidth of nearly 10 to 20 kHz is sufficient to record electrical signal during the tip sample contact period. Therefore, multimodal information of topography, mechanics, and electrical properties can be captured simultaneously.
When we look at the instrumentation and measurements, we find a typical force microscopy consists of an integrated cantilever tip which has assembly of this kind interacting with the sample surface, a detector that measures the displacement of the cantilever, and feedback electronics to maintain a constant imaging parameter such as a tip sample separation or force. The integrated cantilever tip assemblies can have single or V-shaped beams and normal spring constant in the range from 0.1 to 100 units. The most popular and versatile detection scheme in AFM is optical lever deflection. In this quadrant photodiode, as shown in figure 1, force values are determined from the normal displacement Iz or tilt angle 1 theta of the cantilever from its resting position. With an instrument sensitivity of the order of 0.1 angstrom, minimal force in the range of 10 raised to the power minus 13 to 10 to the power minus 8 N, depending upon the cantilever stiffness, can be measured. Hence, AFM can in principle measure molecular interactions ranging from weak van der Waals to even slightly stronger forces. In principle, the magnitude of interaction or intermolecular interactions can be assessed directly in an adhesion measurement. Adhesive interactions between different functional groups is different from the force versus sample displacement, that is FD curves. In these measurements, the deflection of the cantilever is recorded during the sample approach withdrawal cycle. The observed cantilever deflection of cantilever is recorded during the sample approach withdrawal cycle. The observed cantilever deflection is converted into a force using the cantilever constant. the flow chart of force versus distance. What way, when we change the force, the distance from one to another moves. On the right side, the way this graph comes out has been there, and on the other side, it is giving a graphical representation. Slope is the elastic modulus of soft sample or force constant of the cantilever. We'll give a mathematical relations which indicates the two important parameter, that is force versus distance. Adhesion force, which is indicated as F adhesion, is given by a relationship or a mathematical relationship. F adhesion is equal to 3 by 2 pi RW half, where R is the size of the sphere radius and W is the work of adhesion. Adhesion force measurement. Adhesion forces measured under ambient conditions are dominated by capillary forces, which are usually several orders of magnitude stronger than the binding interactions between the fabricated tips and the sample. Roughness of the sample surface affects reproducibility of adhesion force measurement as the sample approaches the tip at different angles during the multiple measurements. Before either a crystal growth rate or adhesion force measurement, it is often a good practice to regenerate the crystal surface by flowing supersaturated solution through the fluid cell to reduce surface roughness. In the case of adhesion force measurement, this can ensure the existence of flat terraces and forces that are free of interference from nearby expertise. Before starting an adhesion force measurement, the supersaturated growth solution should be replaced by the working solution of the lower supersaturation. Work of adhesion, it is called Dupre equation. Work of adhesion can be calculated by the equation which has been given in this slide. The work of adhesion per unit area, that is WA, is the work done on the system when two condensed faces, alpha and beta, forming an interface of unit area, are separated reversibly to form unit area of each of these interfaces. The work of adhesion is defined above and traditionally used may be called the work of separation. For a typical hydrocarbon, the values have been given, and this is what one can always find out. Chemical force microscopy. There are various equations and theories related to this. Johnson, Kendall, Roberts, JKR theory. JKR theory considers the effect of infinite surface energy on the properties of the interface. For external load, that is L external, and internal load, we can calculate the force by the relation which has been given here, where mu is the frictional coefficient, where the area and the forces can be calculated, and with these two mathematical relations, a contact area can be calculated by combining these two, and that has been given as a relation in this slide. External load and internal load can be put together along with frictional coefficient, and a force relation, a relation whereby we can calculate force, has been given. JKR theory, where the contact area of interface can be calculated, has also been shown to be there for this. Applications in nanoscience. The CFM has very many applications in the very important area called nanoscience. A biological implementation of CFM at the nanoscale level is unfolding of proteins with functionalized tip and surface. This is due to the increased contact area. The tip and the surface act as anchors holding protein bundles while they separate. As uncoiling ensues, the force required jumps, indicating various stages of uncoiling. This happens in stages 1, separation into bundles, then bundle separation into domains of crystalline proteins held together by van der Waals forces, and third, linearization of protein upon overcoming these secondary bonding. Information on the internal structure of these complex proteins, as well as a better understanding of the constituent interactions, are provided with this method. A second consideration is one that takes advantage of unique nanoscale material properties. The high aspect ratio of carbon nanotube, easily greater than 1000 angstrom, is exploited to image surfaces with deep features. The use of carbon material broadens functionalization chemistry, since there are countless routes to chemical modification of nanotubes. This happens while the nanotubes are being used with different sizes. Multi-wall nanotubes are typically used for their rigidity. Because of their approximately planar ends, one can estimate the number of functional groups that are in contact with the substrate, knowing tube diameter and number of walls, which help in determining single moiety tensile property. Certainly, this method has obvious implications in tribology as well. Therefore, in short, chemical force microscopy has been used to measure adhesion and frictional forces between probe tips and substrates, covalently modified with self-assembled monolayers that terminate in distinct functional groups. Rope tips have been identified with SAMs using a procedure that involves coating commercial Si3 and 4 cantilever tip assemblies with a thin layer of polycrystalline gold, followed by immersion in a solution of functionalized thiols. This methodology provides a reproducible means for endowing the probe with different chemical functional groups. The spring constants and radii of the chemically modified cantilever tip measurements can be seen. Gold-coated tin, gold-coated silicon, and silicon substrates have been treated with functionalized thiols and silanes, respectively, to produce SAM coated substrate terminating with different functional groups. A force microscopy has been used to characterize the adhesive interactions between the probe tips and substrates that have been modified with SAMs, which terminate with COOH, CH3 and NH2 functional groups in ethyl alcohol and water solvents. Force versus distance curves recorded under ethyl alcohol shows that the interaction between the functional group decreases as follows. We have formic acid, oxalic acid, then ethane, then formic acid versus methyl group. Forced titration of amino group terminated self-assembled monolayer using chemical force microscopy can be very properly carried out. Chemical force microscopy was used to measure the adhesion force between the gold-coated Si3 and 4 tip functionalized with OH groups and a silicon substrate functionalized with NH2 groups. The curve of the adhesion force as a function of the solution pH value, force titration curve, was obtained. The pK half of surface NH2 groups estimated for the force titration curve is 7.4, about 3 pK units, lower than the pK values for NH2 functionality in aqueous solution, and in nice agreement with the values of pK half equivalent to 7.6 determined by conventional contact angle titration. The surface pK half value that we obtain from the force titration or contact angle titration is the apparent surface pK values, which is expressed as the corresponding bulk solution pH values at which the functional group at the interface are half ionized. So students, having learnt about CFM from different angles, in this module we have talked about the instrumentation part. When it comes to that, we have known that chemical force microscopy, which is abbreviated as CFM, is an extension basically of atomic force microscopy that employs a chemically functionalized tip which makes it possible to control chemical interactions between tip and the sample. CFM can be used to probe local chemical information on the surfaces of materials and biological samples under near native environments at nanoscale spatial resolution. The applications of CFM for materials characterization, including measurements of single intermolecular interaction forces and investigations of nanoscale heterogeneity of surface chemical properties of polymeric materials. This finds great applications towards these areas where interactive forces are to be measured at nanoscale domain, that too on a surface which is more of a heterogeneous one between the other two kinds of species. The surface should be heterogeneity of the surface, chemical properties of polymeric materials can also be measured with the help of CFM. Thank you very much, please.